Good morning to all of you and welcome to a new webinar on photonic integrated circuits from our OIP4NWE project and the use of these integrated circuits for different application fields and markets. Today we are looking at the growing area of 5G and 6G applications and the 5G and 6G communication. As always, we have invited an expert in this field to tell us more about this topic. So I will introduce later on Professor Dr. Andreas Stöhr from Duisburg for this meeting. So welcome to this webinar. But before we start, I would like to hand over the microphone to my colleague Maria Trajkovic from the Technical University in Eindhoven for a short introduction into our OIP4NWE meeting, which logo you can see on the slides that we have here. So Maria, please, the floor is yours.
Thank you, Dirk. Can you tell me if you hear well my audio? I had some audio issues. Can you hear me?
Yes, we can hear you.
Yes.
Good. Good. Let me share my screen.
Should be possible. I can stop this.
Yeah. So welcome everyone to this to another webinar. I will quickly introduce what OIP4NWE stands for and what the goal of the project is. First of all, this acronym stands for Open Innovation Photonics for Northwest Europe. And with that said, we have 11 partners who are working on two different aspects of this project. So the partners are based in the Northwest region of Europe with a coordinator in Eindhoven, so Eindhoven University of Technology. And then we have other universities, companies who are participating and bringing forward this project. So two main aspects of this project are revolving around the technology, but also about pushing this technology in the ecosystem and making an open innovation environment in a collaborative ecosystem. So on the technological side, we talk about increasing the maturity and scaling of open access indium phosphide photonic integrated circuits. Then another aspect is providing technology support to SMEs who already have some experience with PICs and want to mature their products. And as mentioned, the open innovation environment is also a very important aspect here. So if we look at the whole chain from the application need to the final product, we focus on these two aspects: fabrication, working a lot on improving the technological aspects. So investing a lot in the equipment to grow the next generation indium phosphide photonic integrated circuits. And of course, working on the packaging, that's another important aspect. So if we talk about packaging here, we mainly focus on optics and integrated optics, and then the full package. Talking about technology readiness level numbers, we position ourselves between 5 and 7. So starting, let's say, with a product which already has a technology readiness level 4, and then we want to mature this product to technology readiness level 7. We are starting from a generic set of building blocks in indium phosphide technology. So we already have developed set of building blocks, which we are trying to mature here with different processes. And that is improving the epitaxy, yield, and stability with different tools, with different application processes. And then increasing also the functionality by introducing new building blocks. If we talk about packaging, what we see here, some of the aspects we focus on are micro-optics and optical fiber arrays. That is on the optical part. Then we have high-speed electrical interposers, flip chip integration, and thermal management and microfluidics on the packaging side. Another important thing, which is now currently very active, is the Innovation Support Fund. So on our website and also on our social channels, we have shared this call for vouchers, and this call is open until 30th of September. So what does this mean? It means that if you are an SME who are looking for an innovation support fund and you have already a design, you can apply for this support. And this support will include the fabrication of photonic integrated circuits by Smart Photonics, external optics design by Vrije Universiteit Brussels, and packaging by Tyndall National Institute. So all these three are included. You will just have to come with a design which is ready. So if you are interested, you can find more information on this link here, but also my colleague Jürgen from UB will tell a couple of words more about this in the end. And with this, I would give floor to the next speaker.
So thank you, Maria. My microphone was still muted, so sorry for that. And thank you for the introduction. And now I want to hand over to our today's expert. As I mentioned before, it's Andreas Stöhr, and I've got a long list with activities he's done before. I only want to mention 2 or 3 of the main aspects of that. So, for example, Professor Stöhr was in the last millennium, I have to say, sorry for that, Andreas.
Danke.
COE fellow at the National Institute for Communication Technology in Tokyo, about 60 gigahertz radio over fiber systems and wireless communication, and visiting professor, that was this millennium, at the University of Ottawa, about terahertz plasmon photonics, and at Corning Incorporated for 60 gigahertz and 300 gigahertz wireless communication systems. Since 2011, he's now a professor at the University in Duisburg-Essen for optoelectronics there, and especially for the microwave photonics and radio over fiber systems and technologies there, and active in that. I don't want to mention the terahertz activities and whatever he's done also for that. And especially since now 2018, I think, he's the also founder and CEO of the Microwave Photonics company, which is also located near to Duisburg in Oberhausen, not so far away from that. And there he is, as I mentioned, the CEO and the driver for this technology. So, Andreas, the floor is yours to give us an introduction in the chips, especially in the photonic integrated chips for the 5G and 6G markets.
Thank you, dear. Thank you very much for this nice introduction. Thank you also for the invitation. Today we are not members of the OIP for Northwest Europe, but maybe we do have some interesting technologies also from the university. So please allow me to introduce the company as well as the university in a few words so that you know in which ecosystem we are working here on, let's say, indium phosphide related devices. As I already mentioned by Dirk, I'm addressing more the photonic side of life. So I will mainly focus on photonic integrated chips. There are other colleagues at the university also working on high frequency electronic chips, but I will come to this in a few seconds. So let me just start this presentation here. A few words about the company at the beginning. So the company was actually founded in 2019, in summer 2019. And we are 3 founders. 2 colleagues from the university joined me in founding these companies. And those colleagues, you can see those colleagues here. These are Thomas Kaiser and Niels Weimann. Niels Weimann is working on terahertz electronics. Thomas Kaiser is working on digital signal processing. So together we founded this company in 2019 in the summer, and the company is headquartered actually in Duisburg. But we do also have a site in Oberhausen. This is what Dirk mentioned a few seconds ago. So since February, we have opened up a new office and lab facilities in Oberhausen, which you can see on these slides here, where the R&D is located within the technology center TZU, which is close to a large shopping mall, Centro, for those of you who may know this, and you see some of the facilities here. So basically this shows here the technology center here where we are located, and then you can see the surrounding area here. And Oberhausen is very close to Duisburg. I think the distance between the university in Duisburg and the company in Oberhausen is only 7 kilometers, so it's very close. Okay, so at the university, also allow me a few words about the university. I am together with my colleague Niels Weimann, who's working on terahertz electronics. The 2 of us share this clean room facility at the UDE, which has a size of approximately 500 square meters. And I will show you in a second a couple of, let's say, instruments which we are equipped in these clean room facilities. We have been able to invest a lot in the clean room facilities in the last years. I'll give you a short overview on that in a few seconds. We are also equipped or very much working on high frequency applications. So that's why we are also equipped with test and measurement systems for photonics, but also for electronics. And as you can see, we do have measurement facilities like network analyzers now operating up to 1.5 terahertz. There are additional equipments, of course, which I'm not going to mention that in detail. If you have any questions, please come back to me. I think we have most what is required in this field. Altogether, the 2 of us, we are 2 professors, about 25 scientists. This may rise to 35 now soon. We have another 10 technicians and about 20, in average 20 students working in our groups. So altogether 50 to 60 people working in this facility here at UDE. That shows you a little bit about the infrastructure, the technological infrastructure that is available here at the ZHO. This does not show you the epitaxial machines, which are on another slide, but I'm just mentioning this here for the sake of time. We have 2 MOCVD machines and also another MBE, all for 3.5 growth. And you see the technologies available, which is now including a lot of technology for packaging, like fully automated packaging systems. We are now having access to special 3D printing machines, also access to milling and other machines, so that we can also do our own packages by various technologies. Yeah, well, that is maybe the, let's say, the technological background that we are working on. And this shows you a little bit about the ecosystem in which we are integrated here in Germany. So ZHO, or Center for Semiconductor and Optoelectronics, is part of the German ecosystem, or not the German, also European ecosystem in microelectronics and photonics. So internationally, we are collaborating with a couple of institutions in Europe. In Germany, we are especially collaborating with HHI and also with Ferdinand Braun Institute, both located in Berlin, but these are just two. There are others. Here we are coordinating a couple of larger research programs. So these are not individual research projects that all of us have, but these are larger research programs. And I'm not going to mention all of them, but maybe a few. If we start here with Marie. Marie is a DFG-funded Sonderforschungsbereich. In English, this is a collaborative research program. And there are only two in electronics or in electrical engineering in Germany. So maybe this shows the impact or the importance of such a project. And it's coordinated here in Duisburg. And the aim here is to develop terahertz technologies for mobile applications. We are also the host, or we are actually the research lab for the German microelectronics fab. And we are especially responsible for the development of electronic and photonic integrated chips for high frequency beam steering. Smart Beam is the name of our research lab. And as I said, we are part of the Forschungsfabrik, which is basically all Fraunhofer institutes in Germany working in electronics and photonics. Altogether, I think it's 12. And there are also 12 research labs, and we are one of them. Then we are hosting the Terahertz Integration Center, which is mainly for packaging activities. That is a funding by the European Commission and local government. We have spun out a couple of companies. Microwave Photonics is one of them. There are others like ID4us, which are spun out by our university recently. We're also hosting the TeraOptics training network in Europe for terahertz research. This is a new ITN that just started. And we are looking forward, or we just hired another 15 PhD students in Europe in order to work on terahertz technologies in that project. For UDE, just a few words, we have 45,000 students. We are still a young university, younger than 15 years, but according to Times Higher Research, we are the 16th best young universities worldwide. So that's a quite high level that we have achieved within the recent years. There are about 6,000 employees here at the universities overall. And in the near future, we are expecting more projects to come. There is another 6G hub in which we are coordinating together with our neighbor universities in Bochum, Dortmund, and Aachen. So the 4 universities have joined the coordination of a 6G hub. This is a larger program, and we are also involved in a Southwest 6G hub, which is coordinated by the Kaiserslautern Deutsches Zentrum für Künstliche Intelligenz, DKIZ, and also KIT, Karlsruhe in University, or KIT Technology. So those two hubs have a funding of more than 100 million euros. Yeah, so this shows you a little bit about the ecosystem in which we are working here. And now I'm coming to the topic, try to be as brief as possible. So I guess you know the use cases that we are addressing in 5G. There are many, but we have now identified 3 major use cases, and they are enhanced mobile broadband. EMBB is the abbreviation that you may have seen. There are other things like mission critical control, in which the latency is the key KPI, so the key performance indicator, which is of importance for mission critical control. And massive Internet of Things is basically how can we connect an enormous number of devices to a mobile cell. This is the question that is addressed by massive Internet of Things. So depending on the use case, you have different KPIs which are of a special importance. So for enhanced mobile broadband, your extreme data rate is the key KPI that you are addressing. For other things like mission critical control, it's the latency. For massive Internet of Things, it's the energy consumption, but also the question how to connect all these devices to a mobile cell. So a little bit depending on your use case, you will have to have the correct technology in place to support this. The frequencies that have been opened up for 5G are well known, most of them, and currently this is the case in Europe. Currently, we are reusing basically frequencies below 3 gigahertz or at 3.5, 3.6, 3.7 gigahertz, which is enabled by harmonized regulations. but it's basically a traditional LTE system or LTE frequencies we are using with a slightly larger bandwidth as compared to the 4G mobile systems. In 5G already we have opened up the millimeter wave frequency ranges for enhanced mobile broadband, especially for enhanced mobile broadband. And there is mainly the 26 gigahertz band or 28 gigahertz in the US, but also higher frequencies in the V band, which is 57 to 64, and in the E band, 71, 76, 81, 86. So those frequencies have also been allocated for special use cases in 5G, already in 5G. This is not on the market yet. You will not be able to buy a base station operating at E-band or V-band frequencies. Most base stations currently operate at 2.1 gigahertz or 3.5, as I just mentioned. For 6G, we have already opened up by two international organizations, like it's ITU and IEEE. Both have opened up the terahertz frequency range for wireless communications and for extreme bandwidth. So here we are targeting extreme bandwidths, and I'll come to that in a second. So this shows you a so-called spider diagram, which shows the key performance indicators of the physical layer that are, let's say, expected for 4G, 5G, and 6G. The inner circle of the light blue is the 4G, the darker blue is the 5G, and for the 6G, basically, we don't know exactly what will be the key performance indicators that we will strive at the end. Let me just focus on a little or some few, let's say, KPIs. I'm not going to touch all, which is the peak data rate. I think this is one of the important KPIs for the technological developments. 4G, we expected a maximum peak data rate of gigabit per second. For 5G, we are expecting 10 gigabit per second and maybe even a little bit more at the end of the 5G phase. Still, we are far away from that with our commercial systems now. And for 6G, the idea is that we may address 100 gigabit, beyond 100 gigabit per second peak data rate, even terabit per second data rate is in the view. And I'll tell you a little bit about that in a few seconds. We can do that already. At least we have already done 100 gigabit per second in the wireless domain. Latencies, another important point, is the peak or the best case that was, let's say, foreseen for 4G is 10 milliseconds. Normal systems can only do 40, 50 milliseconds and even higher. For 5G, we target at 1 millisecond. 10 milliseconds is more realistic with current 5G systems. 6G, the target may be 100 microseconds. Let's see what the discussion will bring out in the near future. And at the end of the day, what can the technology be enabling? And this is also a question of edge cloud computing or edge computing, or even computing at the antenna side to enable such low latencies. Well, we can talk that in a few seconds. Regarding the company, a few words about what we do. We are working on the, let's say, components and the technologies to connect all these base stations by the fiber optic infrastructure. And I'm not going into the details, but you may see this. There are different technologies that can be used for 4G. Most people use digitized ROF. So this is a digitized system in which basically the mobile data is basically AD converted. So it's converted to a digital signal before it's put on the fiber. Then it's sent to the base station. There we have a DA converter going back to wireless and then sending it to the user equipment. This is digitized ROF, which is very much used as a technology, XOR technology, backhaul fronthaul technology in 4G. Already in 5G, there are discussions if we should use again analog, because analog can handle much wider bandwidths. And we also see that this is an interesting solution for many other application fields. We came up with a system, or with an idea to use or to be able to leverage the optical systems by sending only digital data over the optical fiber, but then analog upconversion at the base station. So in our case, if you want to make it simple, then it looks like this. You use digital data communication. This is the standard GPON, EPON optical systems. And then basically we go up to the millimeter wave using an optical heterodyne system. So we have a laser that upconverts then to a millimeter wave terahertz, microwave, any frequency that is supported by the front end. We go on the wireless channel and then to the UE. This allows to use existing optical standards, whereas the analog rough would require some, let's say, proprietary solutions. It may be a good solution for indoor or in-house applications, but not in general. So this is what we are working at, and there are some components, and since this is on components here, we are working on components that are required to enable these systems, like a coherent photonic mixer. And if you see this device here, basically has two optical inputs, and its, let's say, function should be to upconvert a baseband optical signal to an RF millimeter wave terahertz or microwave RF signal. And you see one of the developed components here on the right hand side. This is a CPX, or an upconverter, basically for E-band and V-band frequencies. So basically what you have here is there is one fiber with baseband optical data. There is another fiber that is used for a laser to upconvert to RF. This laser can also be integrated in the package if that is wanted. But here we have it externally, so it can be a tunable laser so that we can upconvert to any frequency which is supported by this front end. And then this device converts to E-band or V-band frequencies depending on the integration technology that we are using. What you see here especially is for E-band frequencies, the maximum output power that we can reach here is 15 dBn. With that system, we can bridge several hundred meters to kilometers of air in order for let's say, for fixed wireless access applications, as I will show you in a second. Other components that we are addressing even go up to the terahertz frequency range. In that case, we have an integration technology that allows us to integrate our chips with antennas and also with lenses in order to achieve terahertz radiation. But we also work on, let's say, more complex front ends. You see a very high gain antenna here, which is then using our components in order to bridge larger distances. So what you see here is a 50 dBi cascade antenna, which is then integrated with the CPX component that I've been showing you in a second before. The components, or let's say the use cases we are addressing, is not only 6G communications, but we're also looking at radar and the medical sector, but I'm not going to introduce you to that in more detail today. Some results which are using these technologies, so this is system level work, but it is using, basically we do the chips, we integrate, we package, we use in the system. And the CPX component, just as an example, which we have used, which I have shown you before, is basically located here. This is the CPX. And the whole system, I'm not going into the detail, just tell you this is an extension. What we do here is we are providing 5G fixed wireless access, so people can use or can get wireless internet access using the conventional optical backhauling, which is in this case a GPON system. So basically you get access to a GPON system without fiber because we use a 5G fixed wireless access technology. So we bridge basically internet into your home using a wireless link, but this is at millimeter wave frequencies which are foreseen for these fixed wireless applications. Currently, this demonstration was done at in the 70 gigahertz band, so E-band frequencies. We use a commercial E-band system that was orange, so we use real data, real antennas. Actually, this demonstration has been done in Poland, and we mounted our antenna on the top in order to demonstrate that we can transparently connect to the internet, to the GPON system from a remote place without changing the GPON technology. The key challenge here was we would not like to change any technology for GPON. So basically the user at the end of the antenna can use the same equipment provided by the operator. He doesn't really know that there is a wireless link in between. So that was the challenge here. This is a more complex system that was demonstrated a few years ago. This is, at least this was demonstrated before 5G was commercial. Here we demonstrated a system that uses a multi-radio access technology in a shopping mall. So we have developed the technology, we have also developed the system, and when we implemented the system in a shopping mall, this is what you see on the right-hand side in the upper picture. This is the shopping mall, and the lines that you see there are the back, or let's say that's the dark fiber in the area. So these are existing dark fibers, and we use this to connect the shopping mall to 3 data centers in the city. This was done in Warsaw. The technology that we are now supporting here is legacy 3G and 4G, so LTE, but we also showed and demonstrated here millimeter wave 5G technology with beam steering features. We also demonstrated fast initial line setup, mobile IP, which enabled us to have an uninterrupted communication link. So that means you are moving from a 5G cell to a 4G cell because you are out of the coverage, but your application will continue. So you do not have to reconnect to the new network technology, let's say from 5G to 4G, but your application is continuously ongoing. You will not notice, other than maybe that the data rate is a little bit lower, maybe your video quality is a little bit reduced when you move from 5G to 4G, but that's all. So the connectivity is still ongoing. That was all demonstrated here in this shopping mall. The peak data rate that we achieved with the 5G systems here was approximately 1 gigabit per second, which is one of the targets for 5G. You see some of the installations here in the shopping mall. These are conventional Wi-Fi antennas, commercial antennas. These are commercial LTE antennas. We really had, since we were connected to 3 data centers in the city, we provided real LTE traffic in this demo. And then we have new E-band of millimeter wave 5G technologies here with beam steering enabled by beam switching. And this was a development of a 5G station developed here by our university, which provided seamless beam steering using a special antenna technology. And it has a fiber optic front haul. So here we have a direct fiber optic front haul connected to the space station, and then also beam steering using in this system. What is also interesting for 5G is if we have beam steering, and if we have to have directive antennas, and this will be even more important for 6G when we go up to even higher frequencies, we need directive antennas. So if then the user is moving, some point we have to localize it. And of course, we can imagine that now we are not only placing a communication system, but we are also placing a localization system to figure out where the user is. This doesn't make any sense. So there is a lot of research work ongoing in order to identify the user, to localize the user with the communication system. And we have shown that this is possible in this research work. We basically use here a 4G waveform, but it's very similar to 5G waveforms. It has a frequency, it's sort of true channel estimation. And we use this channel estimation, which is part of the standard, to localize the user. And we have been able to localize or precisely localize the user. You see that the ranging errors here are below 2 centimeters, and the angle preciseness that we achieved here is around 1 degree, 1.5 degree. So basically we can localize the user with the communication system. We can still communicate, and you see that here we demonstrated that for extremely high data rates of 18 gigabit per second, which is more than what is expected at the end of the 5G developments. 1 second, I think here someone is. Give me 1 second. Hallo? Hallo? Wollten Sie, ich bin gerade in einer Videokonferenz, können Sie die Tür nehmen?
Ja, aber da passt die Schlüssel nicht.
Nee, die Tür ist auf.
Okay.
Sorry, some construction ongoing here in at my place. Yeah, so this is a system that demonstrated that we can also localize the user, and that would allow us, in order to, in continuation with beam steering, we can now localize the user, control the beam, and so follow the user when he's moving. Some other things that we are now addressing is, for example, enabling automatically or semi-automatically controlled cranes here in our haber. Duisburg has the largest inland haber in the world. We are at the end of 2 Silk Roads. So basically we have started, or the haber has started with 3 trains a week some years ago. It's not long ago. Now they are reaching 60 trains a week, and they are targeting much higher traffic on that connections. And space is limited, so the question is, how can we handle this higher capacity? And here digitization is a key issue. So how can we interconnect all sensors? There are a couple of rail gates, trains, ship gates that needs to be connected to the 5G network so that we can control the crane automatically. So basically he picks the container from a ship or from a train and then puts it on a truck automatically, or let's say semi-automatically. This project has been accepted by the evaluators and is now prepared for starting in November this year. Some other issues, we mentioned 10 gigabit, or even the target is to reach 100 gigabit, and we have already reached this target with our technology. This shows you millimeter wave 5G, but we also do that at terahertz 6G frequency of 300 gigahertz. We can reach currently data rates in excess of 100 gigabit per second using our technology. And what is key here is, man, if you look at this upper left figure, it shows you the down converted wireless spectra. And normally there has to be a large guard band. The guard band basically is what you see here. This is the unused frequency range between DC and the lowest edge of your wireless channel. And it's basically, in terms of the spectral efficiency, it's a loss. So here we have been able to reduce the guard band to very low frequencies, and you see that the bandwidth is quite high. In this system, we can we have 12.5 gigahertz of bandwidth. We are reaching 100 gigabit per second now with this system. And we have technology, front-end technologies for 60 gigahertz E-band. We demonstrated that at 60 gigahertz in the V-band. And we also demonstrated that at the WR3 band at 300 gigahertz for 100 gigabit per second and beyond. And what is the latest invention here? This brings me then to the end. Beam steering is a challenge. It's already a challenge at microwaves. It's extremely hard at terahertz, and this I think is the first demonstration of a mobile terahertz system. So we have developed antenna technologies integrated with photonic technologies, tiny chips. You see the size of the chips are extremely small. This is the advantage if we go to terahertz. So that is the size of the chips. Actually, it's only half of the chip that you see here. This is the size of a €1 coin. This is a terahertz transmitter with beam steering features. You see the beam steering that is being able here in this beam pattern profile. And I'm not going to touch all the other details here. With this system, we can now communicate to the user at 300 gigahertz carrier frequency. We have reached more than 20 gigabit of data, and we can steer the beam with a very tiny and fully integrated photonic chip. So that brings me to the end. And so I thank you very much for your attention. And I hope this was an interesting presentation to you. We are not part of the network, but I think we can also be supportive. We do have a lot of indium phosphide experience in chip processing, even growth processing and packaging, especially when it comes to packaging of high frequency and photonic devices. Thanks for your attention. And thanks for the invitation, Dirk.
Thank you, Andreas, for giving us this presentation with these impressive demonstrations. What can be done with radio over fiber and with PICs for the 5G and the 6G applications. So up to now, you were a little reserved in the chat. So perhaps now we want to widen it. So if you have questions, don't hesitate to ask them. You can ask them directly now. So you only have to unmute your microphone that we can hear you. Or you can use the chat too. So Yalma from Photon First asked, should I read it or do you want to ask it directly, Yalma?
Well, I can ask directly. So I was wondering, first of all, it's impressive work and a very nice presentation. I was just wondering if the light from the optical fiber is directly converted by optical techniques, or is there electronics in between to convert the fiber optic signal to a RF signal?
No, it's directly converted. So if I go to this, let me just show this presentation. Someone stop the presentation. I restart the presentation. I hope you can see it again.
Yes.
Okay, so no, we are using direct RF or direct optical to RF conversion in these cases. There is electronics included, let's say for amplifiers and these kind of things. So if I show you one example here, basically this device here, for example, if we look or if we try to look into more details here, I try to enhance that here. So basically what you have here is two fibers coming in, and then we have a balanced photodiode here. And then there is an amplifier between the balanced photodiode and the antenna. And then you have the antenna chip here, which is in this case, because this is connected to a rectangular waveguide. So the output here is a rectangular waveguide. So basically this antenna provides the connectivity between the photonic chip and the rectangular waveguide. So you can directly attach this component to the antenna. So there's nothing in between the optics and the RF, in this case, than a balanced photodiode.
Okay, thank you. Very impressive. And which techniques are used? Can you tell about that? So how does the conversion work? What is?
Okay, so a balanced photodiode basically is two photodiodes in anti-parallel. And if you do your, let's say, your mass calculation, what it is doing is you have two fiber inputs. One fiber is supporting the baseband optical data, and the second fiber puts an optical carrier. The difference, the frequency difference between the optical carrier and the baseband data is exactly the RF frequency. So this is a device which allows you to set any RF frequency within the band that the waveguide is supporting. So here it can be used for the V band and for the E band communications. So the difference in wavelengths between the carrier laser or local oscillator laser and your baseband signal determines the carrier frequency. Then the photodiode converts this heterodyne signal to an RF signal. And since we are using two anti-parallel photodiodes, we are suppressing the DC noise. So this is a system which is very much suited for this wireless applications because it suppresses the DC noise due to the balanced photodetector application. If you are interested, I can forward you some more technical data on how this works. So in general terms, it's called optical heterodyning and balanced photodetector in order to upconvert or to convert from baseband optics to RF.
That would be very interesting indeed, and I think your explanation was already very clear. But if there's more literature to read, I'm hungry for literature always as well. So
if you just drop me an email, I will reply to you.
Thank you. Thank you for answering my question.
We can bring you together. We can send your email data between each other from you, so that you can talk about later on this too. So other questions? If not, then I've got another question. Andreas, what would you do? What would you think? What is the most important challenge for the PICs for the use for 5G and 6G? So where's the most research you have to do?
Yeah. So this is actually a very good question. I try to open the camera so that I can see you better. Where the hell can I do that? Okay, so here you are. I had to change the publication to see the videos. Yeah, where is the major research work? This is a good question. There is two answers to that. One answer is, let's say, if we have this physical layer KPIs, like beyond 100 gigabit or 1 terabit, extreme beam steering technology, this is very much physical layer work. And we have to see here what are the technologies to enable higher output power. How can we integrate indium phosphide terahertz amplifiers with photodiodes, with antenna technologies? How can we make arrays? How can we control the beam? We are currently studying different applications or different scenarios for the beam steering, like leaky wave antennas, phase arrays, true time delays, which is also incorporating work on using silicon nitride technology, actually fabricated by Lyonics, and being integrated here with indium phosphide photodiodes for beam steering, but also from other technologies. So beam steering is a challenge, and this is all, let's say, more physical layer related work. Let's say if we would have, then we do a demo in a system in a lab, we maybe be able to do 400 gigabit per second demonstration in a few years from now. I'm quite optimistic that this will be possible. But then the next challenge is how to make this compatible with a mobile system. This is, I think, an even more difficult problem. First of all, we have to work a lot on enabling real-time operation, and I'm not going into too much details here, but maybe I just mentioned that we have been foreseen for 2 6G hubs in Germany, and this is an investment of more than 100 million euro. In order to enable all this, this is a lot of work, which is then beyond the physical layer technology, and that's quite hard. So how can we enable real time? How can we really incorporate that in a real system? How can we be compatible to the standards? How can we influence the standards so that at the end of the day, we have the technology that then is compatible to the next upcoming 6G standards. So for the physical layer, to make it short, targets like higher data rates, beam steering, controlling of beams, very low latency, how to interconnect with FPGAs or integrated electronics in order to do beam steering in real time. These are technologies, and then the next step will be to see what is the waveform, what are the protocols, how can we make it compatible to 6G standards.
Thank you, Andreas. If there are no other questions from you, then I have to say thank you again, Andreas.
Welcome.
Give us this presentation.
Gerne.
And this presentation is also recorded as the others, and it is visible after this presentation, after this event. You can see it whenever you want at our YouTube channel and at our website. There will you find the link to that. And you've shown the demonstrations and the demonstrators for that one. And perhaps it could be interesting for you too, Andreas, if you ramp up the production of such, or you want to ramp up the production of the components, then we've got also a solution. And that brings me to Jürgen van Erps from the Vrije Universiteit of Brussels. And he will give us now a short presentation about an innovation support fund that could help SMEs to ramp up their production and to have a pilot product also for that. So Jürgen, please,
Thank you very much,
the floor is yours.
Thank you very much. I hope you can all hear me well.
Yes.
Okay, great. And you can see the screen?
You see it also too?
Okay, perfect. All right. So indeed, Marika already briefly introduced our innovation support scheme, but the following presentation will give you a little bit more detail. So as Marika mentioned, we have a support scheme which currently is open for applications. It's targeted towards small and medium-sized enterprises that are located in the Northwest Europe region and targeted to users that want to scale up the production of these photonic integrated circuits beyond a trial phase, so beyond, let's say, proof of concept. We have 7 vouchers available with a support of up to 50 €. And this fund can then be used towards checking design, checking the compatibility with our pilot line, manufacturing the photonic integrated circuits, and foresee it from external optics and packaging if needed. So our call is currently open. We'll close on the 30th of September. And then by the end of November, the winners of the vouchers will be announced. All the information is available on the website, so OIP4NWE.EU/vouchers. And so all the information that I will give here is also available there. So important to notice are the requirements for application. So as mentioned, you should be an SME, you should be based in Northwest Europe region. The TRL of your current photonic integrated circuit should be 4 or higher. So this means that you should have, you know, a validated proof of concept, or at least a design of a PIC ready that is, you know, ready to be scaled up to a higher series production. And then, of course, also in the evaluation, we will require a short business case, which would briefly describe the positive impact of the vouchers on the business case. So either through increased revenues or through the creation of new jobs. And then finally, there's a couple of smaller things. So of course, should comply with the de minimis state aid criterion. And then the practicalities are that the applicant should complete a voucher application form, sign a proxy NDA, and agree to collaborate on documenting the use case, because of course we want to use those voucher grantees as kind of examples of how the pilot line can in the future contribute to their business. So to make the application procedures a bit more straightforward, we basically have 2 application documents. The first one, which is just an expression of interest. So if you think that the call for vouchers is something for you, you can just fill out these 2-pager with very general information on contact details and in very briefly describing your project case that you want to bring forward, such that we can do an early eligibility check towards all the requirements. And if that is positive, then you can proceed to filling out the full application form. Also, that is relatively short, so it's about 7 pages that are foreseen. So again, some contact information details, short project description. Notice also that only the information that is noted with an asterisk is actually going to be used for further dissemination. So that's the only public information that will be requested. All the others is confidential. Then there is a short description on the technical side of the case, and on part B of the document you have a short description on the business side of things. So you should briefly describe the impact on your company's business case and the amount of new business or new revenues and new EU jobs that might result from the project, which basically describes the impacts towards the evaluation board. Then if you submit your application file, we will evaluate the incoming applications. And we have basically those 4 criteria that are scored given a certain weight. And so first is the innovative character of the project with a weight of 1. And then second is the technical feasibility and the quality of the project plan with a weight of 1. The third one is the credibility and the level of commitment of the company with a weight of 2. And finally, the added value on the business case and the potential impact with a weight of 2. And so then all these items are scored. The individual score on each of these criteria should be at least 2.5 out of 5, and the total score should be at least 20 out of 30 to be eligible for the vouchers. And if you are above the threshold, you will be granted the voucher. So that's in a nutshell the procedure for the voucher application. So as mentioned, please visit our website. You can find all the information over there. Or send us an email at voucher@OIP4NWE.EU. If you have any questions regarding the call, then we will be happy to help you forward with the questions that you may have. Thank you very much for your attention.
Thank you, Jürgen. And it's the last call for a question. If it is not,
maybe
sorry,
I can have a question.
Yeah, sure.
I think I'm new to the group, so I may have missed all the previous presentations. What I'm currently missing here is what is the technology which is provided. I mean, there is a lot of let's say work of a funding organization, but since for SMEs, I think most important part is what is the technology provided, not necessarily the questions how to reach any proposal.
Yes. Okay. So that is briefly, let's say, more related to what Marija has presented in her intro presentation. So the technology is based on the indium phosphide platform. Yeah, it's the foundry services provided by Smart Photonics, basically, and then the packaging side is provided by Tyndall National Institute. So that can be any type of thermal management, electrical packaging. Co-packaging with optical components, for example, fiber to chip connection, and from VUB there is a contribution on external optics. So if you have any application on which you would require micro optics, micro lens arrays, or high coupling efficiency features between fibers and your chips, or any of those things, then VUB can provide those.
Do you have something like this? Because still, I mean, these are generic, let's say, technological things, but let's say questions like, what is the RF or 3 dB cutoff frequency of the photodiodes that you are providing? What is the laser? Do you have tunable lasers? What is the output power that you can reach? How about integration, antenna work, amplifiers, integration with silicon nitride? Do you have such a catalog? What kind of technology are you using for mask creation? Is that done by the network, or is it done by the SME?
It can be done by the network, but let's say there is some technical information available on the website, and we can of course further discuss if you have particular.
I just would like to learn what is the provided technology.
Yeah, sure. That's a very valid point. So we'll take it up and see if maybe there is insufficient amounts of technical information available. We can work on that.
I was just speaking as an SME. I mean, I'm also an SME. So an SME,
yeah, sure.
If I am going to invest 10K, then I'm going to invest that into something that is, useful. And so I need to know exactly what is the provided technology. That would be very great if we could do some work in this field.
Yeah. Okay, great. Yeah. That's also, let's say, one of the goals of this expression of interest form is to really get in touch with the people that provide the technology, and then we can organize a call with the technology providers and see if there is a fit or not, and then limit the amount of work done on administrative side of things. So,
thank you.
You're welcome.
Okay. Then thank you to all of you for participation. And now we will have a short summer break. So it only remains me to wish you a good holiday and have a good rest for the next week. And we look forward to welcome you back after the holiday. So thank you for participation again. Have a nice day.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Nice holidays.